Chapter 2 is all about displaying data and different ways of doing that, as well as bias in the data that's being displayed. So for this first question, we have suppose a survey was conducted with participants to disclose their favorite night for a particular activity. And we have our results summarized in this table of data here. Okay, now it wants a frequency distribution and a relative frequency distribution. So to do that, we're going to go ahead and open the data in StatCrunch. Click on that and click on Open in StatCrunch. And that will load up data here. It's going to load it all up in a column here. That's what it tends to do for data. And then with this, we can actually get the both relative frequency and frequency distribution. If we go to stat, I think tables, frequency, and then click on the actual data that's in the column. And then we want both frequency and relative frequency. That's what they're in. They're kind of highlighted there. The rest of them are not. And then I'm also going to store the data in the table so that we can use it for other calculations if necessary. So click compute. And now we have, this is just saying what's there. I can exit out of that. And this right here is the frequency distribution and the relative frequency distribution. So we can see that Sunday was 2 times, and then out of the total times there are, 2 out of that total gives us 0.05. Monday was 3 times, divided by the total. I think there was 50. It was 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So that'd be 40 total. So that'd be 2 out of 40 is 0.05. Yeah. So that works out. So that's how you can use StatCrunch for those things. So let's go ahead and plug these things in. Let me get it all set up here. So we have 2, 3, 4, 5. Then 1, 19, and 6. Okay. Relative frequency. 0.05, 0.75, 0.1. 125, 025, 475, 15. Two, 3, 4, 5, 1, 19, 6. That looks good. 0.05, 0.75, 0.1, 0.125, 0.025, 0.475. Okay, that looks all correct for those distributions. Now, if you own a business that sells products related to the activity, which day would you purchase an advertisement in the local newspaper? Are there any days you would avoid purchasing? So local newspaper, right, is an every single day occurrence. That's typically you get the daily newspaper. And so if you're advertising in the local newspaper, then you'd want to advertise on the day of, so that they read the newspaper and they're like, oh, let's go to this thing today, something like that. Maybe it's not as relevant nowadays, but that's what they're kind of going for here. So the best day to purchase advertising for this activity would be on the day there's most activity, which of course is Friday. That's when the highest number is. And of course, the worst day to purchase it would be when the least amount of time people do the activity, which would be Thursday, has the lowest frequency and relative frequency. So Friday is the best, Thursday is the worst. Okay, now we can construct a bar graph. And to do that, let's go ahead and grab the data again. I'm going to go graph, bar plot, and then with summary. That allows us to have our categories. As you can see here, the categories are, there's 2 var1s because of how it saves the data and how I name this. var1 are the categories, and I'm going to use var1 in this is the second one because it has Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, all only once. The counts, of course, are going to be in the relative or the frequency That's how we get a frequency bar graph. And the rest looks fine, so let's compute that. And this is our bar graph right here. So which one looks like that? We note that Friday is the highest, Saturday is the next highest, and Thursday must be the smallest. So if we look on the graph here, Friday's the highest. Yeah, it has to be A. Friday's the highest, Saturday is the next highest, Thursday's the smallest. That's what it is. Now, relative frequency is done pretty much the exact same way. So let's go ahead and close out of that. We're going to go graph, bar plot with summary, categories in the second var 1, of course, and then we're going to do relative frequency, and we're going to do type relative frequency here. Now if we hit compute, it's pretty much the same graph as the frequency, which is what you expect. Relative frequency and frequency are both like come from the same data, so they're not really displaying different things. It's just what you're talking about. Frequency is the counts, and relative frequency is the percentage that happens. You can see, of course, Friday's the highest, Saturday's the next highest, and Thursday is the lowest. So relative frequency, Friday's the highest, Saturday's the next, Thursday's the lowest. That's the correct one. Now to construct a pie chart, same process. Let's close out of this. Graph, pie chart with summary. Once again, categories are in var 1. And you can do relative frequency or frequency. I think I'm just going to do relative frequency just to see if that works. Compute that. Yeah, looks good. Pie charts typically work on percentages. That's why I chose relative frequency. I'm curious if the regular frequency would work. Let's just try that. It does work, and it actually gives you the percentages here on the side. So it's really the same graph again, no matter which way you do it. You can see that Friday is the largest chunk here in the light blue, and then all the rest of them are here. Of course, Saturday would be the next largest chunk. If we go to the graphs here, we're looking for Friday. Friday is the light blue, which would be D. That's the largest chunk. So that's going to be our answer. Let's check that. And that's correct. Okay, here we have a stem and leaf plot. The stems are 15, 16, 17, 18, 19. The leaves are all the numbers on the right-hand side. Now, 5 in the vertical bar, the stem of 5 and the leaf of 2 means 5.2. So that's how these numbers are read. That means that if you look at this top row here, we have 15.3, 15.4, 15.5, sorry, 15.4 again, then 15.5, 16.1, 16.5, 16.6, 16.8, 16.8, 16.9, 16.9, 17.2, 17.4, 17.4, 17.6, and so on and so forth. That's how the data is read for this specific stem and leaf plot. You can have lots of different stem and leaf plots. This could be where this is the, hundredths and tenths place, and this is the ones place. So it could be 153, 154, 155, and so on. They're just saying which one is correctly shown. Now, since this one is the bar represents where the decimal point goes, 15.3, you can see that C is the correct data. If we were to do a stem and leaf plot using this thing, this is the correct data. This is what that would result in. B doesn't really come from this data because the leaves here are not in this data set at all. This doesn't really make sense. That's not really how a stem and leaf plot works, where they just have these things at the decimal points, 3, 4, 4, 5. That's just trying to confuse you with each one. Each leaf is its own number. That's the key thing to remember here. And then A is a different reading of this graph if it was represented a different way. So like I said, 153, 154, 154, 155. That's just a different way of writing the data. That's not the data that we have, because the data gives us is by the legend. That's how you read the graph. Always use the legend to read the graph, not whatever here. So this data with this legend means that this is the data set it came from in C. Okay, let's move on. The data to the right represents the top speed of all players for soccer league. Construct a relative frequency distribution, histogram, and relative frequency histogram. Okay, so first off, let's go ahead and open in StatCrunch. We have the frequencies here. So now let's create table frequency. Actually, this is easier than that. Really, all we have to do for relative frequency is we need to just compute it. So the first thing we want to know is, let me do it like this. Let me go data, compute, expression. Actually, let's just do it in this column here. We can do it all in one go. Compute expression. What we're going to do is we're going to build the expression. This is how you do calculations in StatCrunch. So everything works in these columns here. So what we want to do is we want to add up all these columns and then divide each one by that number. That's how we get the relative frequency. You divide each count by the number of total counts that there are in the data. So we can do that by taking the number of players, that's the counts, dividing that by the total number. So I'm going to do it by doing the sum, which is the function is going to be right here, sum of the number of players. So what this does is it takes the number of players, it's going to take each cell in this column, and it's going to divide it by the total of all of the columns, so the total number of players total. And it's going to do it row by row here. It's going to put it in this next column. If I hit OK on that and hit compute, you can see here we have the relative frequency of each one of these counts. If we want to create, let's go ahead and plug this data in actually. It wants 4 decimal places. So we're going to get 0.0068, 0.0119, 0.0289, 0.1375, 0.4160, and then we get 0.3989, but that rounds up, so it's going to be 90. All right, so that's the first part there. Now we need to get a frequency histogram. And once again, this can be done as a bar graph. Stat. You could use histogram, but that doesn't, it's easier to just do as a bar graph with the summary. Categories in speed, counts are in number of players, and this is going to be the frequency histogram, not the relative frequency. So you can see the last two have the highest, the second to last one has the highest. That looks like A there. 26 to 30, 26 to, yeah, that's what that looks like. Okay, and now the relative frequency histogram. So we should expect the same thing. It should be D here because that looks the exact same. The last one, the second to last one's the highest, the last one's the next highest. But you can also just do the actual graph, bar plot with summary, categories and speed. This is the relative frequency. Take the number of players divided by the sum of the number of players. And then we're going to do a relative frequency type, compute that. And there we go. You can see it has the percentages here instead of the actual counts. So that's going to give us a D. And it says, what percentage of players had a top speed between 26 and 29.9? Now, what we have here is the frequency distribution. For the percentage, all we have to do is look at the relative frequency. That's going to be 26.2 26 to 29.9. It's going to be this one. This is the same thing as saying 41.6, right? You move the decimal point 2 spaces over. 41.6% of players have that speed between 26 and 29.9. So 41.6%. And then 13, less than 13.9. Less than 13.9 is really just in this first row here. And that's the same thing as 12.068%. Okay, let's check that. It's all correct. Okay, let's move on. Okay, here we have some data, and they want us to make a stem and leaf plot for this. And you can see that out of all these different choices here, the legend says that on the left-hand side of this, or the stems, I should say, are the tens place, and the right-hand side, the leaves, are the ones place. So 4-2 is 42. This would be 42, 44, 45, 46, 47, 48, 49, 49, 50, 50, 51, 51, 51, 52, 52, and so on and so forth. So that's the way we're going to do it, since all these are the exact same, they're the same legend. They all have the same process for doing the stem and leaves. So when we do this, we're going to go ahead and open in StatCrunch. You don't actually need to do this. It's not too hard to do it by hand, but you can do it in StatCrunch. That's what I want to show you. So graph, stem and leaf. Our data is in this first column, and we're going to group by, let's see, the leaf unit is going to be the tens place. Let's go ahead and see what that does. Yeah, leaf unit is the 1. And I think if you do the optional, it'll probably graph it this way. This is kind of the most natural way for it to do it. But you can see that it breaks it up over the lower halves of the 40s and the upper halves of the 40s. 42, 44, and then the upper half is 45, 46, 47, 48, 49, 49. It's how you would round it, right? 42 and 44 would round down to 40. 45, 46, 47, 48, 49, 49, those would round up to 50. The same thing is true here, right? These numbers here would round down to 50, and these numbers here would round up to 60, and so on and so forth. That's how they're breaking it up. And that is the exact same way that these things are breaking up, is over those things. So you can notice that from top down, you always go larger and larger, and from left to right, you're going larger and larger. So B wouldn't make sense because top down, right? This thing has higher values than lower values. That doesn't work out. You can see here at C, we have a 1 here, then 0, 0, 1. No, you always go smallest to largest, left to right. Okay, it could be D or A. Let's see. I'm noticing here that this one has 5 here, 5, 7, 9. This one here has a 5 here, which is not how it's broken up. It's always broken up over the lower half and the upper half, so it has to be A. Just look at the actual stem and leaf plot, right? A is the only one that fits this one exactly. Okay, and as you can see, what we have here is kind of a histogram on its side. So if you kind of like, tilt your head to the right and look at it like that, you can see that the middle 2 are the highest bars, and then the next 2 outer ones are the next highest, and the last 2 on the are the next highest. And that kind of looks like a normal uniform bell-shaped curve. I should say bell-shaped curve. It's not a uniform. Uniform would be a flat line, but bell-shaped curve because it goes up in the middle at the highest and tapers off as you go off to the sides. Check that. And that's all correct. Let's go ahead and move on. Okay, so this is about bias in the data and representing data in different ways. And here we have some data for healthcare expenditures per capita as a percentage of GDP. Okay, for part A, it says construct a time series plot that a politician would create to support the position that healthcare expenditures are increasing and must be slowed. So if I were to look at this, this is increasing, but that doesn't seem very fast. This looks like it's increasing rapidly. This looks like it's increasing, but not that rapidly. This one, of course, goes down and up, and that doesn't kind of show it. So I want this data. So that would be my guess. So to plot this data, I'm going to actually use Desmos. I think Desmos is a better way of exploring this kind of thing. StatCrunch does allow you to plot this, but it's not easy to control the grid. So what I'm going to do is I'm going to open up the data and then click copy to clipboard. What that'll do is it'll open up this thing. You can leave it as tab delimiter. That just means how the data is read by the computer. If we copy this, hit Control C, then I'm going to go over to Desmos, and instead of using the scientific calculator, I'm going to use the graphing calculator, and then go Control V, and that will actually paste the data that we just copied over into Desmos. And as you can see here, it defaulted to this thing here, but we can actually create going from a y-axis of 0. You can see that this is the second set of data, so we have two sets. This is what was the first one? The first one was healthcare per capita. You can see those are in thousands, tens of thousands of dollars, and healthcare is a percent. That's of course going to be between 0 and 100, and that's going to be all based around 15, 16, 17. So this is the second set of data that's really low on the graph down here. And the first set is right here. And you can see that this kind of looks like it's steadily increasing. It looks like it's tapering off a little bit, but it's been increasing quite a bit, and it's still increasing. So that might be what a politician would look at and say, hey, it's increasing and it needs to be slowed down. And that comes from B. So we're just using the data that's actually there. But if we read the data differently, and instead of using healthcare per capita, we use healthcare as a percent of GDP, then the healthcare industry might refute the graph by using a different data. We're using the same kind of data, but different how it's read as a percentage versus just the straight per capita. And that is the second set of data. So let's go ahead and zoom in. That's going to be around 15. So I'm going to change the grid settings to be from 0 up to, let's say, 20. And you can see here, this is the percentages. I could even make it a little bit more relatable, like 0 to 100. That's like the percentages of its actual, like from 0 to 100%. And you can see that it's always based around 2009, 2010, on up to 2015. And you can see that when you look at it this way, it looks like it's not really increasing very much. It's going a little bit, it does jump up a little bit here, but you can't really say it's increasing rapidly because this jump isn't the trend. Like, you're not seeing that trend in this. It's a little bit, but it could go back down the next year, for instance. So this might be what the healthcare industry would use to refute the, whatever the politician says. And that looks like this one here in C. It's all based around that 15, 16, 17% mark. Wouldn't be this one, wouldn't be that one. And that one looks to be like they wouldn't use this one. Like, this does what the data shows, because if I zoomed in on it, let's see, let's go back to the data set. This one goes from 12 to 18. If I do that here, I go from 12 to 18. This one shows that it's rapidly increasing, right? It is actually looks like it's almost exponentially increasing. But that's not what the people would want to show. So instead, they would change the bounds to be from 0 to 18. And that shows a much, much slower growth rate. And so really, it's all about how do you perceive the graph? What scale do you use for the X and the Y axes to display the data in whatever way you want? That's the big thing about the biases. You have to be careful with that. So the scales are used to significantly affect the message. That's what it's saying there. No values have been left out. We're using the same values as per capita or per percent GDP. You could leave out values, but that's not what we're doing here. We're not rearranging the data, and data collection has changed. We haven't changed any data collection. And that's correct. So that's where the scales can really influence how you read and understand data. Okay. 1980 to 2020 or 2012, number of adults in a certain country were overweight more than doubled from 18 to 38%. Okay, so a constructed graph is not misleading to depict the situation. So the best way of doing this is always having the origin point showing, the 0 point. And we're looking for 18% to 38%. That doesn't make any sense. That's like they're both around 30% there. This one's above 20, so that can't be it. This one's not even up to 38. So this is the only graph that's correct. This is about 18%, and this is about 38%. So that one looks about correct. And now construct a misleading graphic that appears more than tripled. Well, out of all of these things, this one appears to be more than tripled. And if you look at that, this one is about 18%, and this one does look to be at about 38%. So this one does have, quote unquote, the correct numbers, but the scale is incorrect. So it actually looks like it's much more dramatic of a change than it actually is. So that would be a good way to mislead people. And that's correct.